Good evening. Welcome to Lesson 2, Ionic Polar or Nonpolar. This is a very quick lesson. I just need to make sure that you can recall that polar and nonpolar refer to covalent bonds. We discussed that in Lesson 1. And I need for you to be able to predict bond type using electronegativity values. You will not have to have any electronegativity values memorized, but you will need to memorize what the difference in electronegativity is expected to be for the different bonds. So we're going to start right here at section 4.3. And in general, the electronegativity values, electronegativity, can be determined or can be used to determine the type of bond between atoms of main group elements. Remember, we're talking about main group elements. The transition elements are usually metallic bonds. If you look at the little visual here, it says right here. I've never used that before. Let's try another one. Okay. Let's see what that does. There we go. Differences in electronegativities reflect the character of bonding between elements. The electronegativity of the less electronegative element is subtracted from that of the more electronegative element. The greater the electronegativity difference, the more ionic the bonding. So if you come up here and look, you'll notice at the bottom you've got nonpolar covalent bonds, which have 0 to 0.3 difference in electronegativity values. So when you subtract the most electronegative element, when you subtract the least one from the most, then if you get 0.3 or less, it's nonpolar covalent. When you do that subtraction, if you get 0.4 to 1.7, you're going to call it polar covalent. It's increasing in ionic character, but it is still a polar bond. It's still a covalent bond. And then when you get above 1.7, you get into an actual ionic bond where one or more are going to actually take electrons and one or more are actually going to gain them. Again, this is a pretty easy concept. The only thing I do want you to definitely take note of is a very common mistake that people make when they first start doing this. You need to make sure that you subtract the less electronegative element from the more electronegative element. It sounds simple, but it is also something that is overlooked and it throws a lot of people. So just make sure you pay attention to that when we start to apply this in a second. So let's finish up these notes and do a little practice. We've got the difference in electronegativity, the bonding character, and the distribution of electrical charge as our column heading. So what we want to look at is if you have a balanced electrical charge that goes along with a covalent bond. Remember, they're sharing equally. And the difference in electronegativity is 0 to 0.3. Now if it's 0, what do you think that means about the elements in the compound? Well, if there is 0 difference in electronegativity, that means that they are the same element. Okay, the next one, if it's got an uneven distribution of electrical charge, then one end has a partial positive and one has a partial negative. If you'll remember, that looks like this. And we talked about that last time. That is also a covalent, but it is a polar covalent because it has poles. If you think about poles and charges and batteries, maybe that will help. And again, this one up here, I can't remember if I actually said it or not, but since they are equal, it is nonpolar. The electronegativity difference here is going to be 0.4 to 1.7. And the last one, when the distribution of the electrical charge is separate completely, meaning you've got anions and cations, and they're attracted to one another, that is your ionic. and it's going to be greater than 1.7 in the difference of electronegativity. That's it. We're going to do a few practice problems and then you're done. Please understand with this, the misconception alert here, the numbers above are just guidelines. These numbers, exceptions do exist as they always do. For example, experimentation has shown that boron trifluoride is covalently bonded even though the electronegativity difference is 2. So it looks like it should be ionic because it's greater than 1.7, but it is not. They have found that out through experimentation. So do understand that exceptions always exist. Okay, so for this last few minutes here, let's make sure that you can successfully predict bond character using a table of electronegativity values, which we have right here. I will always give you a table. You will not be expected to do that on your own. So let's just look at something very common. Let's look at carbon dioxide. Okay, so you'll notice that carbon right here has an electronegativity of 2.55 and oxygen has 3.44. Don't worry about the fact that there are two of them. We are really just comparing whatever the elements in each one are and doing the subtraction problem. So oxygen is greater than the carbon, so it's going to go first. Let me get my pen going here. So it's going to be 3.44 minus the carbon, which was 2.55. So if you want to grab your calculator, pause this for a moment, or maybe you can do it in your head, but it is going to be 0.89. Now we just have to remember that anything that is 0.4 to 1.7 is going to be polar covalent. So this one is polar covalent. Let's do two more, and then I will expect you to be able to do these on a short quiz when you get back to class. Let's do salt for the next one. We've used it enough in class. We might as well use it for this too. Okay. So we've got sodium. Sodium and a chlorine. Now if you look again at your table, let's see, chlorine's right here. It's 3.16 electronegativity, and sodium is 0.82, quite a bit less. So we're going to do 3.16 minus 0.82. So I'm going to grab my pen. It's going to be 3.86 minus 0.82. Most of us can probably just determine at this point it's going to be greater than 1.7 pretty easily, as it's going to equal 3.04. And again, anything greater than 1.7 is going to be, get my right color back here, is going to be ionic. Pretty simple. And one more very easy one. Let's do nitrogen, diatomic molecule. We'll learn that word tomorrow or next time we do one of these. So we've got nitrogen. Where's nitrogen? They're 3.04. I'm just going to write this. I know you don't need this written, but we've got 3.04 minus 3.04 is going to be 0. So therefore, it's going to be nonpolar covalent. Now, if you did not write these down when I did them, I would highly recommend that you find a spot on your notes, maybe over here in this kind of wide margin, and just write those examples down so you'll have something to refer to when you're studying. And again, be ready to do this when you get back to class. Thanks.